Hi everyone, this is your struggling CS student, and today let's solve another LeetCode problem of the day. Let's take a look at today's problem. 2654, minimum number of operations to make all array elements equal to 1. Okay, so you're given a zero-index array nums consisting of positive integers. You can, is 0 counted? Nope, 0 is not counted. And nums of I can go up to 10 to the power of 6, so that's pretty large. You can do the following operation on the array any number of times. You can select an index I that's within the bounds of the array and replace either nums of I or the nums of I plus 1 with their greatest common denominator value. Okay. Return the minimum number of operations to make all elements equal to 1. If it's impossible, return -1. So we can select any index and replace either the number that we chosen or the next number with the GCD of their value, and the GCD is of two integers is the greatest common divisor of the two integers. Then the minimum number of operations to make all elements equal to 1. If it's impossible, return -1. Okay, here it's saying that it can do 4 operations. If we choose index I equals to 2 and replace nums of 2 with GCD of 3 and 4 equals to 1. Now we have 2614. Okay, let's see. Then we can choose index I equals to 1 and replace nums of 1 with GCD 6 and 1, which is equals to 1. Now we have nums equals to 2, 1, 1, 4. Then we can choose an index I equals to 0 and can replace the nums of 0 with GCD 2, 1 equal 1. Now we have 1, 1, 1, 1, 1. Okay, it can be shown that it's impossible to make all the elements equals to 1. The minimum number of operations to make all numbers equals to 1. Interesting. Nums.length is only up to 50. Okay, that's not that large. But it seems to me, if it's possible to get if it's possible to get one element equals to 1, then we can always propagate the action down, upwards or upwards. To be honest, I don't really know the formula for calculating the greatest common divisor between the two integers, but I know that in Python you have like a library that helps you to do that. It's like based on some sort of like math algorithm that I know that it exists, but I don't know how to implement it or how it works. I just know that it works, right? If you import the math library. So, is it really the case that if you have one, you can always propagate it? I think so, because like the greatest common divisor between like 1 and x, it's always 1. I think. Yeah, yeah, it's always 1. So as long as you can make one integer equals to 1, a pair number equals to 1, you can always propagate the action up or downwards. But I feel like this question is like maybe trying to trick you. Why is the acceptance rate so low? We can try a few examples and see if it works. So here, from you just need import math. Return the minimum number of operations to make all elements equal to 1. If it's impossible, return -1. Okay, so there are like a few cases, right? There's the case where nums already contains 1. Nums do not contain 1, but we can find a pairing of elements where GCD of two elements like nums of I and nums of J is equals to 1, then then the then the answer is equal to the length of the input array. Mm -hmm. Verify a pairing of elements. It's not just like a pairing, it's like two consecutive. I can find a pair of elements where nums of I and nums of I plus 1 equals to 1, then the answer is equals to length of input array, or none of the above is true, then it is impossible. Return -1. That would be my strategy. So we can say like counts equal counter of what? Counter of nums, right? This is from the collection library. So we can say like collections counter nums. Okay, so once we have the counter, we can say if counts of 1 is greater than 0, then we can return length of nums minus count of 1. So we can just like if let's say we have already have like a number 1 here, right? Then we can always like propagate the answer here, here, and then eventually here like this. Okay, so this handles the case where nums already contains 1. This handles the case where now we need to handle the case where nums do not contain 1, but we can find a pairing of elements that such that I and I plus 1 is equal to 1. So we can say for I in range of n, let's do it like this, and equals to length of nums. So for I in range of n minus 1, I want to check the pairing of elements. If math of GCD, if math dot GCD of nums of I and nums of I plus 1, if this is equals to 1, then the answer is equals to the length of the input array, so return n. Otherwise, we return -1. Well, it handles these two cases, but I don't know if it's actually correct. Let's try it with a failed input. And let's try random input. Let's break them up. 11, sure. I'm not sure if this is like correct, but we can try it. I think in an actual interview, we probably couldn't use this cheat code. Um, yeah, I should learn like the GCD algorithm um, in the future or soon, because it's not that hard to like memorize the code for the GCD algorithm, and it doesn't take a lot of time to learn it. It's just that I haven't gotten to it. I remember it's just like less than 10 lines of code for this GCD function. But what's the time complexity here? Actually, let's make sure our solution is correct first. It works for this input, but is it correct? I don't know. Okay, apparently it's wrong. So let's see. Ah, I see. Okay. That's because you can perform the operation on the array any number of times. So as for this, there is probably a way such that we can keep applying the math.gcd operation such that we can find a 1. I see. So I guess we can just print this and take a look for this particular input. Because my algorithm makes the assumption that we can only, like the algorithm will be correct if we can only perform the operation on each index once, but if we can perform it multiple number of times. So, okay, then how would we do that? So let's take a look at this example, 6, 10, 15, right? So you have 6, 10, and 15. So between these two, the GCD is 2 and 5. No, the GCD is 2, right? So let's say we replace this with 2. So now we have 2, 10, and 15. Okay, so what's the GCD of this? I believe it's still 2. Answer is 4. In 4 operations, it's able to do this. Or do we replace this? What's the strategy here? Okay, let's say we replace this with 2. Right, now what about this and this? This is 1 times 2. This is 1 times 10. 2 times 5. So between 2 and 10 is still 2. So there's nothing you can do here, I guess, in this case. So let's do the operation here. Let's say it's 2, 5, and 15. Right, so replace this number. Okay, so what's the GCD between these two? The GCD between these two is 1 times 2 and 1 times 5, so this becomes 1. Right, so we have like 1, 5, and 15. Then now we can always, this can be 1, this can be 1, this is 15. And then this is 1, this is 1, this is 1. How many operations is that? You have 1 operation, 2 operation, 3 operation, 4 operation, and 5 operation. There. According to LeetCode, you can actually do this in 4 operations. Okay, let's see. Yeah, maybe we can. So instead of replacing replacing this and this with 2, right? We can replace this with 5, right? So we get 5, 6, and 15. Then from there, like you have 1 times 6, you have like 2 times 3, this is 1 times 5, right? And between these two, the greatest common divisor is actually 1 in this case. So this can become 1. This can become 1, right? And then this is like 5, and this is 15. Okay, then now it's 1, 1, 15. Then you can cancel this, and 1, 1, 1. So that's 4 operation, 1, 2, 3, 4. Interesting. Non-stop length is only up to 50, so maybe we can abuse that somehow. But like, which one do we choose? That's the tricky part. Is this really a dynamic programming problem? Uh, we can choose any index. So what are the options here? I mean, let's take a look. Let's see if we can find like a like a optimal substructure such that it warrants a dynamic programming solution. So your initial state is 6, 10, 6, 10, and 15, right? Okay, so this is the initial state, right? So what are the options here? The options are that, let's move this to the right a little bit. So your options is either you go to this state, which is 2, 10, and 15, and this will represent the operation where we delete 6, replace it with 2. The GCD between these two elements is 2, right? Or we can go to this state, we can go to 6, we can go to 6, 2, 6, 2, 15. 6, 2, 15, that represents the state where we delete this with 2, right? Or we can go to 6, 5, 15, 6, 5, 15, or we can go to 6, 10, 6, 10, 5, 6, 10, 5. Okay, so these are the 4 possible states. Then from here, the GCD between these two is 2. Right, yeah. So we can say, okay, 2, 2, 15. Or we can do like the GCD between these two. Because the GCD between these two is just 2, we can either replace this with 2 or replace this with 2. So in this case, there's only like the same state here. Okay, so you kind of revisit this state at least. But what about this one? This one, you can do like, so the GCD between 10 and 15 is 5. So we can do 10, 2, 5, 15. That's one option. Let's move this to the left a little bit. I guess we can delete this. Delete. Okay. Delete. Delete. We can do here. We can go here, or we can go to 10, 2, 10, and 5. Right, 2, 10, and 5. Replace this with 5. We actually do revisit states. So you see here from this operation, right? From this operation, we can see that like the GCD between 6 and 10 is 2, right? So if we replace this with 2, 10, and 5, now this state is the same as this state. So if we have already solved the problem for this state, we can use the cached result instead. Can use the cached result. But it seems a bit tricky to implement it in a dynamic programming fashion. Because like, how do you keep track of the resulting array? How do you keep track of the array? It's like, it's kind of hard. The current state is not backtracking, is it? No, I don't think so. We definitely can cache the result for a state, but if your state is the array itself, that's very hard to keep track. That's why it's a 1900 rated question. You can perform the the following operation any number of times. Unless there is like a greedy strategy. Greedy strategy. This is 1 times 10. What's the math of GCD of 5 and 10? It's just 5. So actually from 2, 10, 5, is it even possible? Oh, oh. 2, 10, 5. Let's see. From 2, 10, 5, it's possible. He claims that he can make 4 moves. So you can do 2, 2, 5. Then you can 2, 1, 5. Then you have like 1, 1, 5. And then 1, 1, 1. Okay. Okay. I think it's dynamic programming. But it's hard. It's hard. Because like what is your input state? Unless you tell me the input state is like a tuple itself. That's challenging, I think. We can try that. I'm not sure, honestly. Mm, no, but like when do you stop? When do you stop? When is it not possible? They have impossible case, right? I think it's impossible if you can't make any more progress. You can't make any more progress. It can be shown that it's impossible to make all the elements equal to 1. Okay, let's take a look at this case. 2, 10, 6, 14. So you have 2, 10, 6. Okay. Yeah, definitely. Because like the GCD between these two is like 2, right? So you go 2, 2. Then you have like 6, 14. The GCD between these two is 2, 2, 2. And 14, likewise, is 2, 2, 2, 2. Maybe it's not dynamic programming because, well, technically it's possible, I guess, to implement. It can be quite complicated. I think the solution might be more fundamental. At least that's what my intuition is telling me. Um, so we probably want to analyze like all the factors and then somehow make the locally optimal move. I think. So like in this case, you know, for this 6, 10, 15 case, you want to make this move between all of these moves, right? And then you would say, then this you have like, you have 1 times 6 and 2 times 3, and then this is 1 times 5, right? So the GCD between 6 and 5 would be 1, you can like 1, 5, 15, and then from there, the rest is history. You can eventually reach 1, 1, 1. So let's analyze the factors for this input. So you have like 6, 6, 10, 15, right? You have 6, 10, and 15. Okay. You have 1 times 6, you have 2 times 3. This is 1 times 10, 2 times 5. That's it. That's it? I think so. Yeah, that's it. This is 1 times 15. You have 2 times... No, you don't have 2. But you have 3 times 5. Yep, that's it. So the GCD between these two, it's 5. And the GCD between these two, it's 2. Hmm. I was thinking like, what if you just try to make the move that gives you the greatest reduction in number? So in this case, if you have to pick between making this 2, or this 2, or this 5, or this 5, you would pick this option because it reduces from 15 to 5 with a delta of 10. But as we can see, that's actually not the optimal move. So we can't do greedy on that. We can't do greedy on that. Then, mm, is it really dynamic programming still? But how? Because you could say, the optimal answer to this problem depends on the. I mean, there definitely is a DP solution. Hey, really? But the state is the whole input. Oh my god. Can you even cache a tuple? Yeah, you can because it's immutable. Like take up a lot of memory, possibly. Yeah, you probably because like you have a lot of states to keep track of. Let's just try it, since that's the only option that I have. So technically, it allows us to do an n-cube solution here at least. Or can we just like brute force this? Okay, let's see if we can brute force it. 2, 2, 15. Then 2, 2. No, you can brute force it. So like 1 times 2, and then this is like 1 times 15 and 3 times. So like the GCD between 2 and 15 is actually 1, I think. Yeah, then you reach 1 here. Then you can do 1, 1, 2, and 1, 1, 1. So how many operations is that? 1, 2, 3, 4, 5. Okay, maybe it's DP after all. But I think it's too complicated though. Let's try. So you have add cache, def dp, and then the current state is like the whole input itself, but as a tuple. So we have to say like for num in current, I guess. I'm not sure. Return dp of tuple nums. Okay. If you can no longer make any progress, then we're done. If if all the elements are 1, we're also done, right? How do I check that? There's like a syntax in Python that allows you to do like a or check. I just do it like the dumb way. Once is equals to false. False. Okay, so we say if num is equals to, or rather is not equals to 1, then we say once. I guess we can break. Else return 0. Okay. So if it breaks, then this won't execute. So if all is equals to 1 and the break never executes, then 0 will return. Okay, then from there, so this is the base case. Then we say for num in current, we actually need the index actually. Actually can do it like this. This is crazy though. So you say answer is equals to infinity. It's equals to infinity. So this is math.infinity. Then we say dp of the new state. So math.gcd of current of I and current of I plus 1. This is like, I don't know, the result, I guess. Result is equals to math.gcd. Then we say replace I is equals to res it's kind of hard. How do I put the rest of the tuple elements here? Tuple comprehension, is that even a thing? So put res and then current of I or num for num in range of I plus 1 to n. Res num for num in range of I plus 1 to n. Yeah. Replace j, or I plus 1 in this case, this would be current of I with res, then num for num in range of I plus 2. Then we say answer is equals to the min of answer, replace I, replace j, then return answer. Return answer. Really? Invalid syntax. Oh shit. I mean, we can do backtracking. Fuck it, let's just do backtracking. Backtracking would be easier. Maybe backtracking is easier, but I don't think backtracking will pass. So we say backtrack current state, then return. Maybe we need a cache somehow. Okay. So if current is in cache, tuple of current is in cache, we return cache of tuple of current. Okay. Then from here, we need an and again. Okay, for I in range of n minus 1. Holy shit. Replace I is equals to, so we can either set res is equals to math.gcd of current of I and current of I plus 1. Then replace I would be current of I is equals to res. We need the original as well. So say original is equals to current of I, original I. Then we do backtrack our current, then current of I is equals to original of I. Let's not do this first. Then we need to say original j is equals to current of I plus 1. So current of I plus 1 is equals to res current of this bt current and current of I plus 1 is equals to original j. This is a bit sketchy. bt nums this is the steps plus 1, the current step is 0, then we return steps, I guess. Total is fine. So we say total is equals to 0, if all I think that works. Current of num for num in current, if num is equals to 1, then we can record the answer. This is steps. This is the current number of steps. So we say non-local total. Total is equals to steps. Then we can do an early terminate. Really? This is the backtracking code. Maximum recursion. That means that's because we don't have a. We need to do a termination where we couldn't do a replacement, right? Okay, it must have been stuck somehow. Let's take a look. Two, 6, 3, 4. I think it's for this input, right? Is it for this input? Oh, and actually, it's for one of the inputs where we are stuck. If original of I is different from current, if original of I is different from this one, then we can do the backtrack. Rest, same thing here, right? If original is J is different from rest, then we do the backtrack. Really? Well, let's see it works first. Output exceeded. Right, we reach the answer and record the answer. Is it too much? Maybe it's too much. Yeah. It's wrong though. 0? Oh shit. It should be infinity. Okay, the backtracking code works. That's good news. But the bad news is, it's definitely DP because we revisit states. But like, how do we keep track of the current state? I think that's the hard part now. Let's get back our TLE first. Okay, good. So this is the test case to beat. This is the test case to beat. Remove this first. We don't need this actually. This is the base case. So we will return 0. We can say answer. So it's equals to infinity. So if the original is different, we do this thing. Then we say answer is equals to the min of answer and this what 1 plus dt. Okay. Then we need to switch it back. Same thing here. Yeah. Then we'll return answer. Here we return dt of nums. This is the backtracking code, I believe. Steps is not defined. Oh shit. No. Oh, okay. This is infinity. Okay, so this is the backtracking code. Now we want to convert this to a dynamic programming solution because we know that we will be revisiting states, so we can cache the answer somehow. This is a dictionary. I mean, oh, I don't know, man. This is sketchy as fuck. Fuck it. We balling. I don't think it works, unfortunately, because it's like non-stop length is 1950, caching the whole tuple. Oh my god, that's even worse. Hmm. Well, I think it's a valid attempt. I don't know how to solve this problem. But if I had to guess, it's probably dynamic programming. Guess, but we take up so much memory. Uh, and we keep applying the operation, right? So on like very large numbers, yeah, this could get a little bit gnarly. Okay, let's go try. Let's go look at the answer. Topics. Oh, okay. Then this is definitely outside of what I can do because I've not really like learned number theory all that much. Oh, greedy. Okay. First, if the GCD of all numbers is now 6 greater than 1, then it's impossible. Uh-huh. Yeah, we make the same observation. Oh. It's a bit confusing, no? Okay, so here they say that if the GCD of all numbers in nums is greater than 1, it's impossible to make all elements equals to 1. You see, but the GCD of this is 2 and the GCD of this is 5. Then you would think, you know, the answer is negative 1, according to this. But that's not the case. Let's see the code. If G is greater than 1, if the GCD of all numbers in nums, it's comparing 0 and x and then storing that in G. Let's take a look. Let's take a look for case 5. 6. Then it's between 6 and 10 is 2. Then we know. Oh, it's saying between 2 and 15. That means it's always possible to reach 1. But I feel like you need to know, yeah, I need to know, like, I'm lacking the background to solve this. You need to definitely know something about, like, math theory, which unfortunately I don't, but it's a nice try, I guess. Okay, but yeah, that's all for this video. Thanks for watching, and maybe you'll learn a thing or two. I don't know. I guess I can show the solution here. So it's like greedy, and you minimize the intervals to reach 1. Okay, sure, fine, I guess. Alright, that's all from me. Thanks for watching. Have a great one.